You know that moment you first learn to read, or like maybe when you watch a kid learn to read. For a long time, it's just this random jumble of lines and circles on a page.
Oh, yeah. Total nonsense to them.
Exactly. And then there's this incredible cognitive shift. Those arbitrary shapes suddenly turn into a word, and that word just opens up an entirely new world. It stops being ink, and becomes a living idea.
It's a really profound transition. I mean, you stop seeing the individual letters and you just start seeing the meaning underneath them.
Right. But then think about how most of us experienced middle school math. I mean, it rarely felt like learning to read a new world.
Definitely not.
For a lot of us, it felt like being handed a telephone directory in a foreign language and being told to just memorize it. Just this massive, intimidating wall of rules and formulas and symbols with, like, no connective tissue.
Which is exactly where so many people hit a permanent wall with the subject.
Mm.
They end up treating mathematics as a test of short-term memory rather than, a cohesive language of logic. You just try to survive the test and then forget it all.
Yeah, dump it from your brain the next day. Well, today we are taking a completely different approach. We are looking at some excerpts from a really fascinating book. It's titled Math Reboot for Grade 7 Magic Carpet Ride Promotion.
Quite the title.
Yeah, it is. But our mission for this deep dive is to explore why that specific jump from elementary arithmetic to middle school math isn't just a list of harder rules to memorize.
Right, it's much bigger than that.
It is. It's actually a fundamental shift in how we are asked to understand structure and space and relationships. And while this book is technically aimed at 7th graders, the text makes it very clear that this is incredibly valuable for adults who want to rebuild their foundational thinking.
Absolutely, because the landscape of the math changes completely at that age. I mean, elementary arithmetic is almost entirely about calculating how much.
Right, like counting things.
Exactly. You count 5 apples, or you measure the physical length of a desk in inches. It's very visible, very tangible. But the grade 7 landscape, it asks a totally different question. It requires understanding why and how different quantities interact with each other.
Okay, let's unpack this. Because to understand those complex relationships, we actually have to go back to the absolute basics and redefine what a number even is.
Yeah, that's step 1.
And the source uses a great analogy for this. If you are walking your dog right now or, commuting, picture an elevator in a tall building. If the ground floor is 0, going up to the 3rd floor is +3.
Simple enough?
Right. But what happens when you go down into the parking garage? The 2nd basement floor is -2. Those negative numbers aren't fake. They aren't imaginary concepts designed to just confuse you on a test. They represent direction and position.
And that distinction, it really changes everything. Because in elementary school, 0 is the absolute bottom. I mean, you simply cannot hold fewer than 0 apples in your hand.
Yeah, that physically doesn't work.
Right. But in this new mathematical landscape, 0 is just the middle point. It becomes a reference marker. So a number now has this dual identity. It tells you its size, like how many floors you moved, and its direction from that 0 reference point, whether you went up or down.
The book actually ends with this short narrative story to illustrate this shift. It features 2 students named Tuka and Yuna, and Tuka is staring at a math expression. It's 3 minus -5.
Oh, that's a classic stumbling block.
Huge stumbling block. She knows the memorized rule. Everyone repeats it right. 2 negatives make a positive, so the answer is 8. But she's frustrated by it.
Because without the underlying logic, it just feels like a cheap parlor trick. It feels like the numbers are sort of lying to her.
I have to be honest, even as an adult, subtracting a negative feels like a glitch in the matrix to me. Like, why does removing something make the final number bigger? It violates our basic intuition of what subtraction actually is.
It does, yeah, if you're still thinking about apples. But think about the elevator or a number line. Tuka's classmate, Yuna, draws a simple horizontal line to explain it.
Okay.
She says, start your pencil at +3. Now look at the -5. That negative sign implies movement to the left. But the operation you are actually performing is subtraction.
Right.
So subtracting that -5 means you are actively removing that leftward movement.
Oh, wait. So you are taking away the mandate to go left.
Exactly. And if you remove a forced movement to the left, you are effectively compelling a movement to the right. It's like taking away headwind. Suddenly, you are moving forward faster.
Wow. Okay. That actually makes sense.
Yeah. So starting at 3 and moving right 5 spaces gets you to 8. The math stops being this memorized trick about 2 negatives and becomes physical directional movement on a line.
What's fascinating here is how this brings us to the concept of absolute value, which the book heavily emphasizes.
Our absolute value is brilliant because it formally separates a number's size from its sign.
Right.
The absolute value is just the actual physical distance from zero. It completely ignores the direction. So the absolute value of both 3 and -3 is just 3. They take the exact same amount of effort to reach from zero, just in opposite directions.
So once you separate the size of the number from the direction it's traveling, the rules finally make structural sense. You aren't just trusting that a negative times a negative is a positive. You realize the system literally has to behave that way to maintain the physical logic of the number line.
Yes, it builds a foundation of trust. And you really need that trust for the next major leap. Because once numbers have direction, the book asks, well, what happens when we introduce numbers we cannot even see?
The invisible numbers.
Right. This is the bridge from the number line into the world of algebraic variables.
And this is exactly where the math anxiety really spikes for people. I mean, the moment letters start mixing with numbers, Tuka, the student in the story, feels like the letter X is just a fake number. It feels like evasive to her.
That's a very common reaction.
So, her teacher, Mr. Asakura, puts a transparent plastic ruler on her desk.
It's a very grounding visualization.
It really is. He points out to her that even though the ruler is transparent, meaning you can't instantly see a solid painted numerical quantity on it, it still fundamentally exists. It has a specific length that takes up physical space on the desk.
Yeah, you can touch it.
Exactly. So if you line up 3 of those transparent rulers end to end, you have 3x. The X isn't a mystery meant to confuse you. It's just a placeholder for a quantity that exists but is, simply waiting to be known.
Right. A variable just allows us to express a pattern generally rather than specifically.
Yeah.
Let's say you were buying notebooks. Instead of calculating the price of 1 notebook, then starting all over to calculate the price of 2, then starting over for 5.
Which would take forever.
Exactly. You just say the total cost is 120 times X.
Yeah.
That single expression covers infinite realities. It's highly efficient.
Okay, I get the efficiency, but let me push back on how this is usually taught for a second. Because when you actually get to solving equations with these variables, isn't it just faster to use the transposition trick?
Uh-oh. The word trick.
You know the one? Where you just grab a number, jump it to the other side of the equal sign, and flip the plus to a minus. Like if my goal is just to isolate X, why bother with the deep conceptual metaphor of transparent rulers when I can just, jump the number over the fence?
This raises such an important question. Because that magic jumping trick is exactly where so many students and adults, frankly, get completely derailed in algebra. The book spends significant time dismantling the idea of transposition.
Really? Why is it so bad?
Because relying on that surface-level shortcut works for a week or two, but it leads to catastrophic errors later on when equations get complex.
Because you forget the underlying reason the sign flipped in the first place.
Yes, exactly. An equation is not a fence you jump over. It is a perfectly balanced scale. Let's look at the equation 3x minus 4 equals 11. You have 3 transparent rulers, minus 4 units of weight on the left, and 11 units of weight on the right.
Okay, I'm picturing the scale.
You do not simply pick up the -4, move it to the right side, and magically declare it positive. That makes no physical sense to the scale.
So what are you actually doing then?
To maintain the equilibrium, you physically add 4 units of weight to both sides of the scale. The -4 and +4 on the left side cancel each other out. They become 0.
Right, because of that directional movement we talked about.
Exactly. And on the right side, the 11 plus the 4 becomes 15. The scale remains perfectly balanced the entire time, and you're left with 3x equals 15.
Wow. It feels like a subtle difference in vocabulary, but it's actually a massive difference in comprehension. You aren't moving anything. You are applying equal operations to both sides of a structure to maintain a balance.
And if you don't deeply internalize that concept of balance, you will inevitably stumble when dealing with something like the distributive property. Take an expression like -3 multiplied by a group in parentheses, let's say x plus 2.
Right. The classic mistake is multiplying the -3 by the x, but then just dropping the +2 down unchanged.
Exactly.
Yeah.
But think about what the parentheses represent. It's a grouped environment. A good way to think about the distributive property is like sending a party invitation to a household.
Oh, I like that.
The parentheses are the walls of the house. The -3 is the invitation. You can't just hand the invitation to the first person who answers the X and ignore everyone else living there. The operation applies to every single entity inside that house.
So the -3 multiplies by the x to become -3x, and it also multiplies by the +2 to become -6. The whole house gets the invitation.
That's the structural logic at play, which is why the author really stresses the importance of showing intermediate steps. Writing out each operation line by line prevents those tiny silent errors. You are basically making your own reasoning visible to yourself.
Okay, so we've grounded our number with physical direction, and we've learned how to balance the invisible quantities of algebra. Now, the source material asks us to look at how two changing quantities interact with each other in the real world. We are moving from a single static equation into the world of proportions.
Right. Proportions are where algebra really starts to model reality. The text contrasts direct proportion with inverse proportion.
Direct proportion is fairly intuitive, I think. It's like buying ribbon at a craft store. If 1 meter costs $3, 2 meters cost $6, 3 meters cost $9.
Yep, they grow together.
Right. The length and the cost grow together at a fixed constant rate. The formula is simply y equals ax, where a is that fixed price per meter.
But inverse proportion behaves entirely differently. Imagine you have a 12-meter rope, and you need to share it equally among a group of people. If it's just you, you get all 12 meters.
Lucky me.
Right. But if you share it with a friend, you each get 6 meters. If there are 4 people, you each get 3 meters. As the number of people increases, the length each person gets actually decreases.
They move in opposite directions, but in a very specific mathematically matched pattern. The formula there is y equals a divided by x.
Now, in a traditional classroom, you're usually taught to look at these relationships through a table of values, then through a written formula, and finally by plotting points on a graph.
Oh yeah, the endless graphing assignments.
And students almost always treat those as 3 completely unrelated chores they have to complete.
But here's where it gets really interesting. The book has this fantastic revelation. They are not unrelated. They are just 3 different windows looking at the exact same idea. I love the analogy we can use here. Imagine there is a complex, beautiful sculpture sitting in the middle of a room. Looking at the table of values is like looking at the sculpture from the front. The formula is looking at it from the side.
And the graph is looking at it from above. The image you see in each window looks completely different, but it is the exact same object.
Right.
The graph of a direct proportion. The ribbon is always a straight line passing through the origin. But the graph of an inverse proportion, the shared rope, is a swooping curve. You aren't learning 3 different topics. You are just learning to choose the best window to see the pattern clearly.
That concept of choosing your window bridges us beautifully into the chapter on data, because we are flooded with data every day in the real world. News headlines, economic surveys, test scores. But the book points out that just collecting a pile of numbers isn't math.
No, it's just a pile.
Right. You have to find a representative value that actually tells the truth about that pile of numbers.
If we connect this to the bigger picture, this is where we get into the mean, the median, and the mode. And it's a vital life skill, honestly, because people routinely use the mean, the mathematical average, as the ultimate unquestionable truth.
Yeah.
But the mean can be highly deceptive.
The source gives a really striking example of this. Imagine a data set with 5 values, 1, 1, 2, 2, and 20. If you calculate the mean the traditional way, adding them all up to get 26 and dividing by 5, you get an average of 5.2.
Right.
If you read a news headline that says the average of this group is 5.2, you'd assume the group is hovering around the number 5.
But look at the actual numbers. 5.2 doesn't represent that group at all. 4 of the 5 numbers are 2 or lower. That single outlier, the number 20, is completely distorting the average. It's pulling the mean artificially high.
In the context of our previous analogy, looking through the mean window is distorting the sculpture. It's like a funhouse mirror.
Exactly. So you need a different window. You need the median. That's the middle value when all the numbers are lined up in order. So if we line up 1, 1, 2, 2, 20, the number sitting dead in the center is 2.
And the number 2 represents that specific group far more honestly than 5.2 does.
Then you have the mode, which is the most frequent number. Here, both 1 and 2 appear twice, so they are the modes. Knowing which window to look through prevents you from being manipulated by raw numbers in the real world. You have to actively ask, what is this data actually trying to tell me? And is this average hiding the real story?
So we've seen how numbers and data can hide the truth if you aren't careful. But what happens when the physical shapes you can touch and see start lying to you? That is the trap of grade 7 geometry.
Oh, it really is a trap.
The book stresses that in middle school geometry, you can no longer trust your own eyes.
And it is arguably the hardest psychological habit for students to break. I mean, in everyday life, if something looks like a square, we call it a square. If two lines look like they run parallel, we just assume they are parallel. But in geometry, physical appearance is irrelevant. A drawing is just a suggestion. You must move your brain from saying, this looks equal, to this is equal because.
So you can't just stare at a diagram of two intersecting lines, point to the opposite sides and say, well, those two angles look the same size, so I'm just writing that down.
No, absolutely not. You have to declare the hidden structure. You have to state these are vertical angles, and the defined property of vertical angles is that they are equal. You have to prove it by citing a rule.
And the book dives deep into how this challenges our spatial reasoning, especially when we get to 3D shapes. There's a section on unfolding a 3D solid, like a cube, into a flat 2D pattern, which is called a net. You have to conceptually fold and unfold this object in your mind.
Because a 2D drawing of a 3D object on a flat piece of paper is an inherent lie.
Wow, an inherent lie.
It is. The angles drawn on the paper are not the actual angles that exist in three-dimensional space.
The concept of skew lines blew my mind a bit here. If you look at a drawing of a cube and you pick a line on the front face and a completely different line on the back face, they don't intersect, but they also aren't parallel.
Skew lines are a great example of looking past appearances. Think of two airplanes flying in the sky. One is flying north at 30,000 feet. The other is flying east at 15,000 feet.
Okay, I'm picturing it.
If you look straight up from the ground, it looks like their paths cross perfectly. You'd think they intersect.
But they don't, because they exist on entirely different altitudes, different planes of space. They will never touch, but they aren't parallel either.
Exactly. To understand skew lines, you have to rely on the stated conditions of the math problem, not your visual impression of the flat drawing.
So what does this all mean for actually doing the math? This brings us to the practical advice the book offers for writing tests and proving your knowledge. It tells the reader to literally draw on the diagrams. Take your pencil, mark the equal angles, mark the parallel lines.
Yes, map it out.
Turn the empty picture into a map of confirmed facts. And when you solve a problem, explicitly write out the conditions you are relying on.
That advice goes far beyond just scoring points on a middle school test. This is the very beginning of formal mathematical proof. The author is actively training the reader to banish the phrase "it looks like" from their vocabulary.
Which is huge.
By explicitly writing out the conditions, you are building a logical chain of reasoning. If you don't learn how to justify your spatial thoughts structurally now, the advanced math in grade 8 and grade 9 will simply collapse.
It all circles back to that idea of reading a new language. You have to understand what the grammar is doing underneath the sentence, or you are just repeating sounds.
The grammar is everything.
So let's bring this all together. Rebuilding a math foundation as an adult, or trying to master it for the first time as a 7th grader, isn't really about memorizing the formula for inverse proportion. It is entirely about organizing your thoughts. Mathematics explains itself incredibly badly when it skips its own reasons. When we just jump to 2 negatives make a positive, or we just jump the fence and change the sign, we are skipping the underlying reasons.
We are memorizing the phone book instead of learning the language.
Slowing down to understand the why, visualizing that transparent ruler taking up space, mentally balancing the physical scale of an equation, finding the honest window for a set of data that is what turns a terrifying wall of symbols into a connected, readable world.
It's the realization that math isn't a collection of arbitrary traps designed by teachers. It's a consistent, logical system designed to describe reality accurately. And actually, that leaves us with a final thought to mull over as we wrap up.
Oh, let's hear it.
We just explored how grade 7 geometry forces you to stop trusting your eyes. It demands that you prove why something is true based on verifiable structural conditions, rather than just trusting a surface appearance. So, if true mathematics is fundamentally about looking past what seems true to find what can be logically supported, how might applying that exact same grade 7 geometry mindset change the way you consume your daily news, or how you evaluate a political argument, or even how you navigate complex problems in your everyday life?
Man, when you learn to read the world that way, looking past the surface to find the real structure underneath, that's when the random jumble of lines and circles finally turns into a language you can use. Thanks for diving deep with us today.